All right, let's get started. So, we would like to start the whole talk with a little thought experiment. So, I would like you to think about a system that I would like you to design or like suggest a design for. You can use pretty much anything you want. I have a few, very few specifications or rules or things I want you to comply with. And apart from that, you can do pretty much whatever you want. So I want you to design a system that will be counting a number of people going in and out, say, this room. So, for example, you have something outside counting the number of people going in and out. There are very few rules that I want you to comply with, and these are those. So I want you to comply with quite a strict privacy policy, so I don't want the identity, faces, whatever, of people passing by to be leaked. I want you to design a system with a quite high performance, so it should work for one person, for 10, for 100, it should work. It should work also, it should be quite quick. So whenever anything happens, I want to know about that, and I want to know about that when it happens or right after it happens. And I want it to be relatively cheap to run. So those four things. Apart from that, you can do whatever you want. So while you're thinking about that, we'll say a few words about ourselves.
Hi, my name is Tannaz. I'm working as a head engineer for the University of Oslo, where we are building an open source cloud solution for research and education sector in Norway. In my spare time, I'm helping IT communities and playing around with IT devices.
And my name is Rustam. I am a chief engineer in a company called Computas, also in Oslo, Norway. I work a lot, mostly with Java, so IoT and stuff. This is kind of the things we play in the spare time. So I work mostly with Java, mostly with architecture and stuff like that. On a spare time, I run also communities. I run, amongst others, a cloud developer community in Oslo. And I'm also a Java champion and Google developer expert for cloud. Okay, back to our example.
Yeah, because I think maybe we can solve our problem with IoT devices. These devices are cool, accessible, easy to set up, and we can connect several sensors to such devices. So maybe one of those devices can help us to count people.
Exactly, and that was our thought. That was our first thought when we were trying to build this kind of thing. Today we would like to talk about our journey, like where we started and how far we got, and explain you about things and the concepts that we had to learn about, and we kind of suffered so you don't have to. And so to begin with, we'll probably need to do some kind of introduction of these concepts of IoT, IoT Edge, and stuff like that. So this is a typical stack. This is kind of our definition of this stuff. So on the bottom there, you have an IoT devices that are generally marketed to you as smart devices, things with network connectivity and sensors. We'll get back to that very soon and explain what it is in a few slides. So on top of that, you have IoT Edge devices that have a little bit extra. Again, we'll get back to what and how and things. And on top of that, there will be also fog and cloud. So, and as you might have guessed from the title of this talk, we'll be spending quite a bit of time with IoT Edge. So we decided to split that thing up into a software that runs on them, the hardware that they're consisting of, and also the architecture of the devices itself, and how you should put them together and stuff like that. So let's start from the bottom, I guess.
Yeah. What's IoT in general? We can say that IoT is the connection between our world and the digital world. So these devices have internet connectivity. They collect and generate massive amounts of data, send data over the network to some servers or cloud for processing, and then receive the results. But there are also some challenges, because as internet connectivity is growing so fast and mobile technology is improving so quickly, our lives become more and more dependent on such devices. And well, as the number of these devices grows so fast, the security challenges and privacy concerns that may affect our lives will also rise. However, we can say that such devices are great because they give more access and opportunity to more people.
And well, when we talk about the devices, number of devices growing and everything, I really like this slide because it's, it's not just saying, well, the things are growing, there will be more of those things, and that's it. It actually also compares it to some other things because, for example, on the bottom there, the blue, the dark blue thing in there is the number of computers. And you see it's actually slightly declining, and they're expected to decline a little bit. And then you have smartphones, smart TVs, smart home devices, and all the other things. But then this big gray thing in the background, which is the general kind of IoT devices, is growing much faster and much more devices. So the speed and the number of devices is quite different. Obviously, those devices have like positive and negative sides. So there are some positive things that they bring to the table. So since there's so many, and they're being produced more and more, they're getting very cheap to produce. The size of the devices is getting really smaller and smaller, so they're getting very, very tiny. And also, they are usually very specialized to do what they are supposed to do. Like, they're doing one thing, and they are quite good at that. In addition to that, they will also provide things like some kind of positioning thing, so tracking, so accelerometers, GPSs, you know, things like that. So it will be packed of tiny little sensors, and they're very small and easy and everything, and it's kind of very, very nice. Well, like, apart from not so nice things, I guess.
Yeah, as I mentioned earlier, security can be a challenge because when we are talking about IoT devices, we are talking about many devices. So we have more like different hardware and software that can have potential bugs. And then privacy can be an issue because in most of the cases, we send raw data over the network to some servers, and both servers and network can leak data. As we are talking about lots of hardware devices, so that can be complex to how we can interact and communicate with each other. And, well, environments can also be an issue here because we have to think about the environment, how we can recycle those devices. Mm-hmm. And, well, those devices, in most of the cases, are dependent on internet. So if we don't have internet connectivity, we cannot use them. Well, IoT Edge. If we want to explain a few words, we can say that it just improves operations and it's cutting costs. But, well, we need to have a definition for that. As IDC says, edge computing is a mesh network of micro data centers that process or store critical data locally and push it to a central data center or cloud. So edge computing allows data produced by IoT to be processed on the device locally. IoT computing typically sends data somewhere else for processing, while edge computing keeps most of the data on the device and do most of the processing on the device. So it means that such devices have their own compute, network, and storage locally, just in a smaller factor.
And before we go any further, before we go to the next slide, I really want you to hold on to one thought. And that thought is, edge computing is a mesh network of micro data centers. So think about that for a second, and in a few slides we'll get back to that. Just hold on to that thought, mesh of micro data centers. All right. So I guess we've mentioned positive and negative sides for IoT. So maybe we should mention also positive and negative sides and things that kind of IoT Edge is trying to address and compared to IoT, just regular IoT devices. So those devices are, well, obviously they don't have to send much data back and forth. So they don't really have to rely on a system or on a some kind of servers being on the background and trying to figure out what those devices has to do. So you will, it will be much faster, and also if and only if you implement it correctly, it will be also helping you with your privacy issues, because then you can just keep the privacy or sensitive data on the device and do something with it, anonymize it, remove things from whatever you don't want to have there before sending it somewhere. And that will help you with these things. And also, it will give you a real-time availability, real-time data transmission, basically all those things that you get because you don't have to send things back and forth. And in general, productivity increase, because sometimes you it's not about just making it's nice to have things. Sometimes you just are not able to provide enough bandwidth or provide enough storage to collect all this data. I mean, we're working with the projects where you have a boat, a huge boat with a bunch of sensors in the middle of nowhere with a tiny little satellite link sending things over, and you cannot send all the sensor data all over the boat through that little uplink. So, but not all things are perfect, right? Again.
Yeah. When we are talking about edge computing, in most of the cases, we are talking about one device. So there is no redundancy. If we lose our device, we lose our data. And if our device fails, so we have to replace it. But if something like this happens in the cloud, we can just replace it, or we can just start a new virtual machine. So it's quite fast in the cloud, but not in the edge. And when it comes to security, there are two different arguments. On one side, we can say that it is more secure because there is less data in communication with third parties, less data. We send less data over the network, so that's great. But on the other side, we can say that it is less secure because the device itself can get attacked much more easier. So in designing such devices, we have to think about how we can use the access control using VPN, and we have to remember to patch and update our device more often.
Yeah, and it's probably a very good idea for whatever you're creating, actually, but well, that's another story. Okay, so the devices, what you normally have at home, like things like that, you have some kind of assistants, you have some smart lights and everything. In most of the cases, there will be some kind of an IoT device, which will be collecting all the data, sending it somewhere, and, well, waiting for it to be processed and getting back some kind of, usually they call it intents or something, well, for example, for the assistants of different kinds, they will be like, you ask it to do, and then it will think and guess what you ask it to do, and then return and try to do that kind of thing. The problem is that all those things are sending data somewhere, and we've seen issues with more or less all of this kind of known devices that have been out there that where the privacy and the data has been leaked into that. And it's kind of a bit sad, and at some point you kind of start going in that direction. Give you a few seconds to read. Right? I mean, it's it's a little bit kind of sad when you're like, who's listening? But don't worry, we have a solution for you because, well, actually, it's not us. We just found a solution for you. It's obviously XKCD that has a solution for you. So you can do this when you come to visit anyone. Yeah. So this is actually the way of, well, detecting if somebody's listening because, well, you know, there will be some purchases of, what was that thing? Creamed corn, 2 tons. Yeah, that's perfect. But, okay, let's go back. So those devices, and what usually happens is that you pull up your phone, you click on a light app thing, or whatever, it will go to the gateway, it will go to the cloud, it will come back to the gateway, it will come back to the light, and it will do the thing you asked it to do, to turn it off, turn it on, change the lights, change the color, whatever. And this is an issue because you end up giving up some information, and you don't sometimes want to do that.
No, I mean, the functionality is really great, and these assistant things are really helpful, but the problem is when they are connecting and combining this information to a specific person, time, and location, right? They could, in most of this, they can run all those processing things on the device locally to protect both data and privacy. And that's a problem. We don't need to share that information with the whole world when we are waking up, when we are going to sleep. So,
well, I mean, there is a lot of articles and stuff on the internet about this kind of thing. So we're not going to need to go really deep into that. But we're just mentioning that it's the kind of thing that you consider when you're developing. Because, I mean, I suppose that you're here either because you're working with those devices or you would like to work with those devices. So think about things like that. Think about privacy and don't collect or send much more data than you need to. So now we've had IoT Edge. Now it's about time to mention a little bit about clouds and fog. How many of you have heard of fog? 1, 2, 3, yeah, 3 hands. Okay, good. That's kind of pretty much that's what we've seen in most. Just to check if your hands are working, I usually do that. It's fun. Clouds, anyone? Yeah, okay, so your hands are working. That's a good thing. It's always good to check if it's like you're actually following. So the fog, the short story of the fog is, remember I asked you to remember that thing, the mesh of micro data centers? So the fog is this thing that connects all that mesh of micro data centers, and that's where the fog computing thing comes in. So then where you can actually kind of spread the load between those tiny little computers, because, well, technically they are tiny little computers. They're not just things with a bunch of sensors and just network connectivity. It has some more. It's a tiny little computer. I mean, you have one example here that we'll be looking in a bit. Yeah, so
Yeah, just to sum up these terms. Edge computing can be any devices such as wearable devices, sensor, network systems, and so on. While fog computing is the network here, is the network that is needed to transfer data from its device to its final destination. And, well, cloud, which is someone else's computer.
Yeah, that's
so
pretty much it. That's the cloud is easy to define now, right? So, okay, now that we have the definitions and everything, now let's have a look at these things that we had to, now we had to choose a device, choose what to run on it and stuff like that. So, to do that, we need to go back to our example, the thing that we started with, and we kind of asked you to think about a system with a very few requirements. So, the 4 requirements: privacy concerns, identity and stuff of people, performance, so high performance, low latency, and low cost. Okay? Right. So first, we needed the device.
Yeah. So most of the cloud providers have already thought about that, and they have their own hardware. Both Microsoft and Google have a hardware for that, while AWS has an operating system that can be run on Arduino-ish devices, such as ESP32. And there are some other alternatives that are more general, such as Raspberry Pi, Banana Pi, Arduino, but they are not really meant to run machine learning on top of them.
Mm. And they also have, I mean, technically you can also mention that AWS has this car thing that is a camera and the computer and everything, but I'm not sure if it actually classifies to be, well, it is kind of an IoT Edge device, but it's a bit like it has wheels and stuff, but, well, yeah.
Yeah, talking about machine learning. So we have to mention that edge computing, compared to the cloud, has a limited resources. So we cannot compare these two things together. And running machine learning and deep learning on top of that will slow down the process. To bridge the gap between edge computing and the cloud, there are some companies that have already thought about that, and they're building purpose-built accelerator devices. And these devices have a tiny chip that we are going to talk about that will take over the most expensive and complicated part of the calculation, that will speed up the process, will free the CPU, and now we can use the CPU for something else. And this is what is great with such devices.
And we'll see in a bit the difference between the CPU and this little chip thing. But first it's kind of worth mentioning a few AI accelerators that are out there that are available so you can use. Well, one of them is made by NVIDIA Jetson. So it's a tiny little computer, small one, tiny, running Linux with some extra hardware that can do neural networks and process things. There is also one made by Intel. It's NVIDIA's Myriad chip-based thing. It's a USB accelerator. I have it in, well, it's in my bag right now. I forgot to take it out and put it in my pocket. I usually do that. Sorry about that. It's right there. I'll show you in a bit. It looks like, well, a little bit smaller than this. It looks like an old USB stick, where you remember you bought those with, yeah, well, the size of it is an old USB stick. Well, anyway. And then you have, and you can plug that into any computers, into Raspberry Pis, your own laptops, or anything, and it will be helping you to take over the load of doing the neural networks and everything on that USB thingy. So then you have also Google with their Edge TPU. And it comes also in, well, that one actually comes in 2 flavors. So there is a USB accelerator, so similar kind of thing to Intel's. So it's a thing that you plug into your computer. And then there is a separate computer, which is a dev board. This is more kind of meant for prototyping. That's the one we ended up using, and this is the one you see here. So it looks like this. Most of the magic is happening on that tiny little board under the fan, under the cooling, and so that's where the CPU and the connectivity and all those kind of things sit. So it's a system on modules, some. And below there, it's basically expansion kind of ports and everything where you can connect your HDMI connectors and network and things like that. But that thing is the size of a Raspberry Pi, but then it has a little bit extra what Raspberry Pi does not have. It's actually pretty much the same hardware as Raspberry Pi as well. So that one has a TPU, and TPU stands for TensorFlow Processing Unit, which lets you run TensorFlow-like jobs on that thing quite easily, and it will be much better at running this kind of hardware on relatively weak hardware. It will run pretty well, because the thing is that not all TPUs are like that. You might have heard about TPUs before, but I'm kind of sure that's probably not those. You might have heard about these ones, and those have a tiny little bit different size. So this is a picture I took in San Francisco at the last Cloud Next, Google Cloud Next, and this is that person is, he was taller than me. And that thing is huge. And, well, that's not just one TPU. So the whole TPU rack, Google's TPU rack, is 8 of them. So hardware-wise and power-wise, it's two totally different things. But that's not the point. If you really want to run heavy jobs, do that. Be my guest, whatever. Put it in the cloud and share it. But if you want to do it locally, if you want, because of the privacy, because of the costs, because of things, this is your probably a better friend. Yeah. I guess we need to go back to our example and...
Yeah, the implementation of our experiment here.
Yeah.
So to do that, we needed to learn some machine learning terms, because here we have lots of data. The time is important. We want to run it really quickly, as Rustam mentioned, and it can be complex because we have many people moving in and outside. So we had to learn what classification, detection, and tracking were. So classification is when we know what kind of object we have on an image. And in detection, we can see our object and we can localize it so we know the coordinate of that object. And tracking is quite like detection, but the difference is that in tracking we have series of images. So we have to do both classification and detection in tracking. And we have to remember what kind of object we are talking about. So I can, just to explain it here a little bit better here. So in classification, we see that we have puppies and not kitties. In detection, we know what kind of puppies we are talking about and where it sits. And in tracking, we have to remember what kind of puppy, what exact puppy we are talking about.
And where it is in a picture.
Yeah. And just tracking is much more complicated. So before we explain that, we can show you some examples of classification and detection.
Yeah, because the thing we're talking about now, it's a very general thing. So I just want to mention that. We've landed on using the Coral for our toy project, pet project. Whatever, you can use whatever you want, and you'll probably have the same kind of issues building that. So most of it is very, very generic, and very few things are. So your mileage may vary. It worked for us, might not work for you. That's why we kind of try to show a little bit of the differences as well. So we have a tiny little video. I can play that thing. I wonder... we have a live demo of that as well, but just in case, we ended up, so you start a server. So we actually created a tiny little server on this device that will serve up a simple web page and a bunch of pages. And we have images of dogs and a few cats. So hot dogs and dogs. And for those of you who know this app, like Hot Dog Not Hot Dog app, so this is kind of the thing we tried to implement. So here we're actually showing the examples of a detection and classification. So with the classification, it actually says, well, I see a pug on this picture. And the certainty is, well, 0.97, I think, so 97%. And with the detection, we actually show where it is as well. So we see, okay, well, here we see a person, and we see also a dog. And that dog is a Chihuahua. and also, well, so here we're using two different models, and also the interesting thing is that those two different models have been trained on different objects. So one of them, classification, has no concept of a person or a koala. So if we do a detection, it will, I think it should say koala bear. No, actually, if you do detection, it says it's a dog. And if you do a classification, it will say it's a koala bear. But that's because, that's also, I think it's a good example, because it shows you that your model has to be trained to recognize things that you're running it on. And if it does not know what it is, it will still try to guess. And, well, koala looks like kind of a dog, I guess, an Australian dog. I don't know. And please don't try to Google wet koala. It's scary. It will haunt you. Don't do that. Just wet koala. You'll see this cute little bear thing. It will haunt you at nights. Don't do that. So I've done it. Don't do that. Okay. So going back to our example. So you have a video, right? So you have some kind of camera connected, like in this case, we have this tiny little thing connected to this, and you're streaming video to the device. All the way since the animation concept was invented by this guy called Edward Maybridge in late 1800s, it was actually it was just a set of images followed after each other. And what changed is actually the speed of how often these images change and the size of the images. So this is one of his first animations. You probably have seen this kind of boy riding a horse, I think it's called, or whatever it's called. It's usually on the like round thing that turns quickly in front of a camera and gives you like the impression of the horse moving. So the idea is, a video is nothing more magical than just a stream of images. To detect a thing on an image, so running detection is quite CPU intensive, but now you have machine learning models that will do it much easier, and you don't have to use much of the CPU power on a small, tiny devices like this, or maybe even more powerful devices, but still, you don't have to have like a huge monster machine to process just one video feed because of the costs, because of the power consumption, because of all those kind of things. The tracking part, though, is not that easy still, because now you have to remember things between frames. So you have to remember things between images. And it is a bit tricky. So, for example, you have an image or a video of 10 seconds, and you're filming at 30 frames per second. So you have 30 frames, 30 images a second, and it's 10 seconds video. So you're sitting there with 300 frames. And on those 300 frames, there are two people moving. If I ask any of you here in the room, I'm pretty sure you'll be very likely to be able to say, well, yes, I've watched this video of 10 seconds, and I've seen two people there, cool. If I ask computer that, it has no idea. He was like, okay, two people, two people, two people. So he might have as well say, I've seen 600 people, because, well, it's images. So you have to do this kind of thing. You have to remember things between frames, and you have to correlate them, and you have to try to guess. You assign different IDs to objects, and then you have to actually follow those objects between frames. So if those people are moving, and there is a third person appearing there, it should actually know that, well, that was their ID 1, that was ID 2, and ooh, this is the third one appeared there. And you have to do that very, very fast, because...
Yeah, this is the 4 main steps that we do for our experiments. So we start from capturing an image, and then we resize our images because our machine learning models use a specific size of those images, and then we run processing. When we have the result, we display it. And that should be, I can show you in the next slide. This is a system in action. So we are running a train model on person, and we can see how accurate it is. So we are actually more human than the picture on Rustam's access card. And we can also see that here the inference time is 8 milliseconds, and we have captured 120 frames per second. So it means that we go through all those 4 steps just in a few milliseconds for each image. So that is really fast.
Yeah, 8 milliseconds, that's fast.
Yeah, maybe we should show some examples. What's the difference
We
between
can
CPU and
do
CPU?
an example. So this is an example of, so you can see there, it says, I don't know if you can see, it's Sometimes resolution is a kind of funny thing with YouTube. We'll play it again. Let's see. No matter how many times you actually show it or refresh it, it will still be, come on. Okay, so now we're running it on TPU. It's a lot of cars, and it's actually able to detect that. And it's doing like 80 frames per second now. Now we switch to CPU, which is basically the same CPU that you will find on exactly actually the same CPU you'll find on a Raspberry Pi. And it was super slow. And now we switched back to TPU. So you see that the difference in performance is quite amazing. And again, we're not talking about super powerful computers here. We're talking about a tiny little thing that costs, well, a few thousand kronas and, well, a few hundred bucks. And it's not a super data kind of computer thing. Well, we have all those things live, so we'll be showing you in a second. But first, we would like to tell you this thing that about like our experiences, the thing we've seen. Well, obviously, we've seen that you need to implement all those things that we mentioned already. But there is also a few kind of things that are very obvious right now for us, but it was not very obvious when we started with this kind of project. We've been playing with this thing for almost, well, a bit more than a year now. And we started when it was like just arrived to beta. So it was a lot of things that we kind of need to figure out. It was emails going back and forth, trying to figure out, trying to understand, trying to go through the code, trying to decompile code and look at things and, you know. So the thing we realize is that the various models, you will have different models, as we've already seen in one little tiny demo, different models will have different performance. So since you're doing those things many times a second, that matters. It doesn't matter if it's like 100 milliseconds or 80 milliseconds for you if you do it once or twice. But if you do it many times a second, it does matter. Don't put much code into synchronous functions. That thing I learned the hard way. We were about to do a demo at the Google's office in Oslo, and just 1 hour or 2 hours before we were supposed to do this talk, I was debugging some code, so I put like print statements all around the code, and I tried to print tensors. So tensors is like huge matrices that they use in machine learning. So I did print those. My performance went from 120 milliseconds to 2. That's just a print statement. That's it. And it took me some time to figure out what it was. So, well, another thing, obviously, optimize everything. And this is probably the coolest slide you will see in this presentation, because we have screenshots of, oh, that doesn't go away. Oh, now it's, so we have screenshots of Snapchat. And, well, it's written in the region, but I guess you can read that. But basically it says, when you have 1 gigabyte of memory and you're trying to compile a huge C library, and you add 16 gigs of swap to that thing. So this happened to us. We were trying to compile a very big C library for this tracking and correlation of frames. And that thing spent like 5 or 6 hours compiling that little piece of code that actually on a regular computer would probably be in like 2 minutes. It took us 5 days and numerous of tries to make it work. At some point it worked, but it was very weird and confusing. This is, by the way, not the correct way of doing that. You can do it in a much better way. We figured out later, but well. So you wonder if it was actually smooth sailing, because that's the other cool thing we all see on the slides. We actually use emojis because that's cool, right? So in reality, it was not really like this. It was a bit more like this. So it was a little bit thunderstormy. It was a little bit like, you know, waves and things were happening to us. And then this is the actual footage of us sitting there late at night and evenings after work, our pet project, you know, you do it after work. So yeah, that was us. That's how we looked. As yellow probably as well, because we kind of forgot to eat and drink and stuff. And then we learned things, and then it kind of became smooth-ish sailing. So now you know your in and outs in the code. Now that thing just came out of beta in, I think, October or November or something. So now that one is much well supported. There's more examples, there's more things. We know much more things about it, and then we can play around and build more and cool kind of demos on top of that. What we did actually, one of the first things we did, and we didn't talk about this thing here, in this presentation, but you can also train your own models on that device. And we did that last Easter. We actually made that thing to recognize Easter bunnies, eggs, and chicken. So you would give it an image, and it will say, hey, I see an Easter bunny there, or I see a chicken there, or I don't see anything here. So you can train your own models, and it was just like 30, 40 images of each. We just used the scraper to download those images, put it in a folder, let it train for a tiny little bit of time, and there it was. So it's actually really nice. And
we should maybe mention that the device itself is not the case here. Because in our case, that was the easiest device that we could get to start with. We tried several devices that was really hard.
Yeah.
And
we did.
You can choose whatever you want.
We did try the device, and we started with an Intel's, and the first requirement, and that was in 2019. It was less than a year ago-ish. The first requirement there was that you needed to run 16.04 Ubuntu. And we were like, okay, thank you. And the problems just piled up from there. So that was the coolest device for us. Your mileage may vary again. So I guess I will do this. I will put up let's
do the live demo.
Let's do the live demo now. Oh, there is a chain. Those things are chained together. That's really nice. We're doing another thing that you're not supposed to do in a presentation. We're actually switching computers in the middle of the presentation. So it's a very, very dangerous move. We're kind of hope we have enough karma from the demo gods. It almost worked. We just need to do the mirror display thing. Oh, wow, it worked. Amazing. Keep this configuration. Yes, please. So we have two demos here. First one is this web app. So, and here you can actually see what's happening on the server side and on the web interface. So we refresh. And we are getting, this is not the main page. This is the main page. So we have a bunch of dogs and a few koalas and a few cats, because that's what's on the internet, right? So if we pick a classification, it actually says, well, I think I see a pug. I'm not very sure about the results. Well, because I wouldn't be sure either with this kind of hairy thing around the pug, as if they don't have enough hair to begin with. Well, we can zoom in. Ooh. Okay. CSS. That was me doing front end, so that's why the CSS is flaky. It's a good thing I'm not front end developer, I guess. And then you can do a detection. So the difference is that you can actually see if it is where it is and the coordinates. So you have the bounding box here. And also you know what it is and how certain it is. So it's certain, like 60% certain, right? The cool thing is, I want you to show this. This is kind of interesting, because if you take this image, and you remember I told you that classification model I'm using has no concept of human. So it doesn't know. So if we do a detection, it will actually say, oh, well, I see a person there. There is a yellow frame around it, right? But if we do classification, it actually says something weird and something really interesting, I think. It actually says it's a dumbbell. Do you know why? Can you imagine why? How many of you have seen people in a gym doing the shoulder press thing? So the machine learning is like, oh, I've seen this thing before. Usually it involves dumbbells. So it actually says dumbbell, because it doesn't know the person thing, right? It doesn't know the rubber thing or whatever. It's just like, dumbbell. So it's actually a good thing to consider and to remember that your models might give you some kind of false positives sometimes if they're trained on things that you don't really want them to be trained, or the other way around. So yeah, that was, I guess, yeah, and on this side, in the backend side, you will actually see if we do classification, you'll see this little joke that I put in because, well, I don't know, just for myself. We have this kind of detection. If it is a hot dog, which that one obviously is, versus not a hot dog.
Wow.
So yeah, the Silicon Valley app, it's present here. All right, we have a few seconds, I guess, and we can do one last thing. We're gonna do the live demo thing that usually, the demo gods are funny with us. Let's see. We lost the connection, so we need to reconnect. Here you go. So I think we'll start with 80%. So this is our system that we have been playing around with. This is the final product. Oh, we need to have the front end as well. There it is. So now it actually is able to detect if it can see people or not. So now it actually can see one, and then you turn around, now it were two. Cool. And then we can do this funny thing that usually works very, very poorly.
I think it's too dark here, but
it's probably too dark, but we can point at.
It can actually count people.
What we figured out is that we need to. So the command line here, I can make it bigger, and you can see what's happening.
Oh, we got light.
Yeah, thank you. So what's happening here, we're just starting a server, we're providing model, we are providing some labels to it, and we're filtering just person, we just don't want to have anything else. And we're providing a threshold of 80%. So we're at least 80% human. The thing what happens is that usually if we run the same model against the audience, here, it will be, no. So with lots of trial and error, we realized that there are differences, like all people are equal, but some are more equal than they're, I guess, like, well, you know, the humanity fact, I don't know, no, it's just a bad joke. But, with 30% certainty, we're actually able to find out a lot of people. Yeah, there is a lot of people. And the thing is, it's a bad camera, it's bad lighting, and you're kind of far away. And normally when you count people, they're a bit closer and everything. So you need to adjust your model a little bit. But, you know, it kind of works. And I guess we're running out of time. So the one last thing I really want to do is to show you our contact information. So in case you have any questions or any comments or anything, you are more than welcome to ping us. I guess we need to do. Oh, this is two screens are fun. Yeah, there you go. So this is our contact information. Thank you very much for coming, and well, feel free to stop us and ask any questions. Thank you.